Okay, let me talk about a little bit of middle school physics, torque balance. Here's the general formula: F1 L1 sine theta 1 plus F2 L2 sine theta 2. Add until F. If you have n different forces applied to the lever, then you will have F plus up to F and Ln sine theta n. So those terms are not necessarily all positive. Of course, it won't be because the right hand side is 0. So we need to determine if it's going in one direction and the other going to the other direction. For this whole illustration, I will define the clockwise as a positive. So let's look at the one of the general scenario using with a definite center of rotation. So a lever doesn't necessarily need to be straight. So here is just a wiggly lever. Then we have a center of rotation here. We apply force on this way and apply force on that way. This on the other side as well. So if the way to calculate it is basically connect the dot of the center of the rotation with the point where the force is applied. Here's a line. The length of the line will be L1, and the angle between this L1 line of L1 and the direction of F1 will be theta 1. And if you try to imagine that intuitively, just there's a center of the rotation, you tilt it this way, then you can think you will find out that this pen or this lever will rotate counterclockwise. Since we define the positive direction as a clockwise, then this term should be negative. So thus we have negative F1 L1 sine theta 1. Similar idea, we apply F2 here and connect the center of rotation with the point of where the force is acted. Here is a L2, and the angle between L2 and the force F2 is a theta 2. Then we define then that just again as we said, this one, if apply force here, it will go clockwise, which is positive. Then we ended up having this torque balance equation: negative F1 L1 sine theta 1 plus F2 L2 sine theta 2. So intuitively, let's think about what the sine theta contribute to this equation. So let's imagine a scenario. We have a center of rotation on one end, and we give it theta equal to 0, which means the line is parallel to the force. So we basically give like this. As you would imagine, it doesn't give the lever any tendency to rotate, so there's no torque. And on the another extreme spectrum, we have theta equals 90 degree, which is the lever perpendicular to the force. Then if you can imagine, if you put any force down, then this will rotate clockwise. Then all of those torque being used, there's no waste. So since the sine 90 degree is 1. So as you remember, our sine theta is a symmetric from 0 to 90. Then it's from 90 to 180 is the same, but just like a mirror on this way, which means if you take the angle on this like this, theta 1, or take the angle of 180 degree minus theta 1, is the same. It's the same number like this. So most commonly we have 4 different scenarios. Technically we only have 2 scenarios, but let me just start with the easiest to the little bit harder ones. So the first scenario, we have a lever. The center of rotation is on one end. The force going down. F1 is pushing it down. The F2 pulling it up. So as you can see, as we do the same thing, the center of rotation, the point the force is acted, the line is L1, same to the F2, the line length is L2, and as you can imagine, as you can see that the L1 and F1 is perpendicular, and sine 90 degree is 1, so we just spare ourselves with calculating the sine theta. Then now we need to determine the sign of each term. So we can imagine the force going down. This pen will go clockwise, which is that means as we define the positive clockwise, then this term is positive. On the other hand, if we're pulling it up here, then the pen will go counterclockwise. Then this term will be negative. So we end up having F1L1 minus F2L2 equals 0. And this scenario 2, we have center of rotation in the middle, and we push it down on one side and push it down on the other side. Same deal, we have center of rotation where the point the force is acted here and here. So the length is L1 and L2. Again, in this scenario, we have L1, F1 are perpendicular to each other. L2, F2 is perpendicular to each other. So we don't need to worry about sine. The sine theta. Since sine theta is 1. And if we can imagine, if you push it down on the left hand side, the pen will tend to rotate this way, which is counterclockwise. So it should be negative. So negative F1L1, and this will be positive F2L2. So since you can think it will go clockwise this way, then there will be minus F1L1 plus F2L2. So this and this is a similar scenario, but with angle and the not straight lever, which is added to the complexity, and those two are pretty similar. So let's look to this. So we have a lever that is bended a little bit, and we have a center of rotation here, and force F1, force F2, and we connect the dot of the center of rotation and where the point the force is acted. This length, this straight line length is L1, and the L1, the line has an angle with F1. That angle is theta 1. Similar here, center of rotation, F1, F2, the point where the force is acted, F2. The length will be L2. The L2 have angle with F2. It's theta 2. So, and also now we need to determine the sign of each torque. So this, if you can imagine, it's going, if you apply F1 here, it will rotate counterclockwise, so it should be negative. So it will be negative F1L1 sine theta 1, and this will go clockwise if you apply force down on the right hand side. Then it will be plus F2L2 sine theta 2. So the last one, we do the same thing. I believe now you already know the drill. Connect the center of rotation where the point of force is acted, center of rotation force is acted. Then we'll have L1 and L2. The angle between L1 and F1, L2 and F2, theta 1, theta 2. And we determine the sign. If you push it down like this, it will be going clockwise, so it will be positive. If we go counterclockwise like this will go counterclockwise, then it will be negative. So we end up getting F1L1 sine theta 1 minus F2L2 sine theta 2.